one question, of course, is how can we track the movement of this electron, right? Or this lack of electron, this hole? As we said, we could track it by tracking the movement of every other electron, right? You could write the equation of motion for all the remaining electrons in there. That's the very basic way of doing it. Just to say, well, there are about 10 to the 22 electrons or something in that order of magnitude electrons, and write 10 to the 22 equations of motion for these things. And of course, you have to deal with the lattice, so you have to deal with all the remaining electrons, and there's a whole lot more. So it's somewhat complex, beyond my ability. Maybe you guys can. But then there's another way of thinking about it, is to think about it as a particle itself with a different mass, an effective mass of the whole, or and call it the whole, and say, well, it's like a positively charged particle. Now, in our analogy, you can think about, how would you track the movement? Let's say I give you a physics problem. Say I have a water tube filled, almost filled, with a little bubble in it, and I tilt it by 20 degrees, 10 degrees, and please predict the trajectory, or the velocity, or the acceleration, or the x, the position of this particle over time. How would you do that? Think about it. It's a very basic mechanics problem. Now, if you are a fluid dynamics person, you would go nuts if I asked you that question, right? Because you would, you won't go nuts because you don't know how to solve it. Well, the thing is that you exactly know what the problem, how complex the problem is, and then you will try to solve it very accurately. And then it becomes very difficult. Because essentially, if you want to do it very accurately, you have to track the motion of every water molecule, or at least treat the whole continuum. But there's another way of solving it relatively accurately, not exactly, but get a very good approximation of what's going on, and that's to treat that bubble as a particle with negative mass in this case, because the force is gravitational as opposed to electrical. I will have negative mass instead of negative charge. And if I treat it as a particle with negative mass that experiences some drag force in the water, I can predict the motion of this bubble quite accurately. And that's exactly what we do. We treat this as a positively charged particle with a different mass, with larger mass, with a larger effective mass, which accounts for the drag, due to the fact that it's not as easy to move it as the electron in free conduction band. But nonetheless, that's the way we treat it. And it's an approximation, like a lot of other things we'll do, and a lot of things that we have already done. Right? Engineering deals with a lot of approximation. It's making the right approximation at the right place. So you can get to so you can make the problem tractable, so you can analyze it, so you understand what the trade-offs are, so that you can go back and get around those and design around those. Okay? And we'll see that more and more as we go forward. Now, okay, so we said all of these things to see if we can predict what is a semiconductor, what is a conductor, what's an insulator, right? So, in this microscopic picture, what is a semiconductor? Or let's say, what is an insulator? How would you tell if something is an insulator?
It has a very big energy gap.
Right. Why does it have to be big?
Because since it is an insulator,
why a small energy gap is not enough?
because if it is smaller, then any small amount of energy can take the electron from the valence to the conduction pattern.
Okay, so fewer electrons have enough thermal energy to pass that barrier. There will be a few, always, no matter how big it is. But they're small enough so they can't carry a whole lot of charge. And that's why you don't have an ideal insulator. There is no such thing as an ideal insulator. Because there are always a few of them that are hot enough that get up there. But there are so few that you don't care about them for all practical purposes. But is that enough? So let me show you a counter example of what you just said. Imagine that you have and you can think of many of them. So these are the two energy bands. This is the conduction band, and this is, let's say this is a large enough band. Let's say this is, I don't know, 5 electrons, 10 electrons. Here. And this is filled, and this is half filled. Is this a conductor or an insulator? It's a conductor. It's a very good conductor. Because these electrons can move very freely. right? They have all they need to be able to move is just to have this much energy difference to go up to this higher level and then move around. And there are a lot of them, so they will be all distributed in energy in the band. There's a lot of free space for them. They move around. That's the way, if you take a piece of sodium or potassium. That's the way it works. It has one electron in the outer energy level, I guess in the conduction band, in a steady state. So it doesn't have to be excited from the lower energy band. So to have a good insulator, you need to have two things. One is what you just said, which is to have a large energy band gap. The other thing is to have a half empty, completely full and completely empty valence and conduction bands respectively. Okay? So it's not enough to have just a band gap. But that's an insulator. That's how you get an insulator. How about a conductor? How do you get a conductor? Well, one way is like that. The other thing is that you may sometimes have overlapping bands.
Yeah.
There may be no band gap, or a band gap is so small that you have at room temperature, everything is up there. I mean, a lot of them are up there, not everything. So you can see that in this picture, you can actually have a better understanding of what a semiconductor or what a conductor and insulator are. So what is a semiconductor? A semiconductor is one with an empty conduction band, at least at 0 Kelvin, but with a band gap which is not too large. So at room temperature, there is a fair amount of these that can go. I mean, not a whole lot of them. So you want a band gap that's high enough so this is not completely full, but it's not as high as that of an insulator, right? And that's why I said a semiconductor is more like a bad insulator, not a bad conductor. Right? Because it's an insulator with a smaller band gap. So it should be a semi-insulator for you. If you call it that, people will laugh at us. They should. Okay. So we understood the concept of the conductor and semiconductor. And also we have a basic understanding of what the hole and electron are. Of course, you can write this mathematically, you can analyze it, and again, if you're in a solid-state physics or device physics course, well, probably more in a solid-state physics course, you will talk a lot more about this. A lot, but you won't. I mean, so that's the basic picture. You think about it as a problem for the purposes of what you want to do. But, so we can make this piece of semiconductor, fine, but is it very useful? Well, it's still one bulk of material, right? It's one chunk of stuff, right? And you can't do a whole lot with that as is, so fine. It's a poor insulator, or it's a poor conductor. How's that useful? Not really. Poor conductor. If you want to make a resistor, you can make it out of it. If you want to be a really bad resistor for reasons we'll see later on, extremely sensitive to temperature. But we'll talk about that extensively later. But so I need to do something else to be able to kind of unleash my creativity, to be able to play with this. I need to be able to make a change. Maybe I have to be able to induce a change in the properties of the semiconductor, where and when I need it. So what is the important property of a semiconductor? It's the conductivity, or the resistivity, I guess, right? So one thing is the question of how can I engineer, can I modify this conductivity or resistivity? How can I do that?
By inducing more electrons.
Introduce other things into the pure structure, right? Because right now, so far I've been talking about a pure piece of material. A solid, clean, pure piece of silicon, crystal, perfect crystal, right? Silicon. But now, what if I introduce other kinds of atoms? So let's say the basic semiconductors we deal with, or the pure ones as opposed to compound ones, are usually column 4 elements, right? So this is column 4 of the periodic table. This is column 3, column 5. So let's go through. What is the first row of the column 4? Of the third, fourth, and fifth. This is carbon, right? Talking about 6. Talking about. What is 5? Boron. And how about the fifth column? Nitrogen. Right. And then below that you got silicon. What do you have here? Aluminum. Yeah. And what do you have here? Phosphorus. Now, below that, you got germanium. You get gallium here. You got arsenic. Below that, I think you got tin. You got antimony. Is it? No, it's the other way around, right? And what's here? Indium, yeah. So, the ones we are most interested in, obviously, is this guy. And the dopants that we usually talk about are these two and that. Oh, sorry, yeah, not that, sorry. That's what causes the problem as a dopant. Boron. So, let's start with the carbon 5 element. Let's say phosphorus or arsenic atom. And both of them are used and they behave slightly differently from a processing perspective, but for our purposes they are the same. So I'll just treat it as a carbon 5 element. And let's say I go back to that basic picture of the lattice that I had. And so let's say this is a silicon lattice. Of course, a two-dimensional picture of the 3D lattice. And they're all silicon atoms. Except for this one. So now let's say somehow I change one of them. I take one of these silicon atoms out, and I put a carbon 5 element there. Let's say phosphorus atom. Or arsenic, let's say arsenic. And so what happens now? Now arsenic has 5 electrons in its outer shell, right? As opposed to 4. So 4 of them form covalent bond with silicons around. But the 5th one is kind of an orphan in a way, right? So what you have here is a 5th electron. Oh, sorry. 5th electron. Which is attached to this arsenic atom. Right? But for all practical purposes, the rest of this arsenic atom, what is the charge, the net charge of the rest of this arsenic atom? What is it? Plus E, right? Because you have a minus E and there is conservation of charge. So, what does it look like to you? I mean, from a first order perspective. The relationship, the interaction between this single electron and this plus E. Looks like something we talked about half an hour. Kind of. What is it?
Electron hole pair?
No, simpler than that. Earlier. Very early on. Hydrogen, right? Well, it's not hydrogen, but it kind of, from an electrostatic perspective, there's a plus E, there's minus E, but there's a difference. Now, this thing is not in vacuum. This thing is in silicon. So what would change in that perspective? Let's go back here and look at this. There's this electron, let's say the mass is the same, and the electronic charge is the same, of course. Planck's constant is not going to change, hopefully. And but how about epsilon? Now I'm not in vacuum. I'm inside the dielectric. What is the dielectric? It's silicon. So now this has to be multiplied. This has to be really the epsilon. So it's epsilon r times epsilon naught. So this energy level gets scaled by epsilon relative squared. What is silicon's epsilon relative? It's about 11.7 or something like that. So this energy level gets scaled by 11.7 squared, something like 130, 140. So now, the difference here is that now I have a similar structure in terms of bonding of this electron to the atom, to the arsenic atom, this 5th electron. However, it's very loosely bounded because the energy level this time now is approximately some the order of minus 0.1 eV, minus 0.1 eV divided by m squared. So even the base state has an energy of only 0.1 eV. It's quite low. So this is a loosely bounded electron, unlike the other 4 that are tightly bounded because of the covalent bond. This 5th one is very loose. can be very easily knocked off. With a little bit of temperature, raising the temperature, just a little bit of thermal energy releases this electron. And so that can happen much more easily than the other electrons. So in the energy band diagram perspective, if this is the edge of the conduction band, and this is the edge of the valence band. By the way, from now on, I'll just show you the edge of the band. So when I draw a line and show EB, I mean anything below that there's a band, and above that there's a band. Okay. So this corresponds to a different energy level now, right? Where is that energy level? Think about it. It's an energy level with a small change, with 0.1 eV energy, extra energy. I can release an electron into which band?
Valence.
Conduction, right?
So it will just
It becomes a free electron, right? Like that. So it has to be close to this guy. So this energy level is here. And when that happens, so I release this electron is releasing to the lattice. So it's happily moving around. There's a difference this time though. So when that happens, so I release an electron and I have an electron here. I have conservation of charge, obviously, right? That's very fundamental. And that means that there will be a positive charge here, plus E, right? But is there a difference between this case and the previous case where I have just thermally generated electron?
No hole.
No hole. Okay, good. That's true. But there's a difference between the type of positive charge that's left here and the positive charge left there, right? What is the difference?
One's immobile.
Exactly. This one cannot move. That could move. This one doesn't. That's a charge carrier. This is just a localized ion. That's the difference. Now, this is interesting because of this subtle difference, I can have more electrons now than holes. So I created one electron without creating a hole. In a pure piece of semiconductor, I could not do that. Every time I created an electron, I created a hole as well, right? I couldn't do one without the other. They went hand in hand. And this time, I have created one extra electron without creating one extra hole. And I have, of course, a localized charge here to balance the charge, to guarantee charge neutrality, but it's not moving. And that's why this energy level associated with these donors, by the way, these are called donors because they obviously donate electrons, are shown as a broken line here, not as a solid. To demonstrate that, to emphasize the fact that they're localized. So this is an ED. This is the donor energy. Okay. Now, all right. Well, if it works one way, it might work the other way too. So what if I introduce a column free element into the lattice? What happens then? Think about it. Well, let's just make this column free element. That's the beauty of whiteboard engineering. Make modifications very quickly. There's another kind of engineering discourse called PowerPoint engineering. A lot of people are now experts in PowerPoint engineering. They do very nice PowerPoints about engineering, but they actually ask to build it. Because sometimes you have a little bit more problem. Okay, so let's say I introduce a boron atom here. Now, the boron atom has only 3 electrons in the outer shell, right? So there will be one dangling bond. One missing bond. So, but this thing can be easily filled because another bond close by next to it can break and form a bond here. So this electron can move from here to there, and then this guy can move from here to there. So this thing, well, it can move around, and it has a positive charge, a plus E. And of course, when you have the 4 electrons on the outer shell, you have an ion, so you have minus E. So you have charge neutrality as well. But now, this time, it's the positive charge, the hole that I've created, that can move, right? So the hole is mobile this time. And the electron and the negative charge is not. It's localized. So now this is an acceptor because it accepts an extra electron. And where would that energy level be?
Just above the valence.
Just above the valence band. So in this case, instead of this, I can have an energy level here. And what happens is that as soon as I raise the temperature a little bit, I leave a hole, and then this goes in there and gets ionized, and the hole can move around. So now I have two methods of changing my semiconductor. I can make a semiconductor that has more holes than electrons, and I can make a semiconductor that has more electrons than holes. And I can control the number of holes and electrons that I will have by controlling the density of these extra guys, these dopants. So that's called, this process is called doping. Okay? Now let's go back to this picture of the undoped semiconductor for a second. Let's talk about something. Now, what was the cause of this whole electron hole generation? Thermal energy, right? So now there's thermal energy, right? So this they can keep over time you generate more and more holes and electrons, I guess, right? Does that mean that if you wait a very long time, you will have a very large number of holes and electrons? No. What happens?
Recombination.
What does that mean?
Some of the holes and the electrons will combine with each other and that will.
Yeah, initially, let's say you're at 0 Kelvin. As you raise the temperature, you start generating more holes and electrons, right? Then you have, after a while, you have some electrons and some holes, an equal number of holes in this case, right? But they're moving around. So every so often they come to close vicinity of each other, one of the holes and one of the electrons, and they recombine. And all it takes to recombine is this electron to fill this hole, and they both disappear. That's recombination, as you pointed out. So in steady state, what can I say about the rate of generation and rate of recombination?
Equal.
Should be.
They have to be equal, right? That's by definition the steady state. Otherwise, I will generate more, and then the number grows, or I recombine more. Well, let's go. R is equal to G. So, rate of recombination, rate of generation in steady state. Okay, but so now you see that at room temperature these are ionized. But now how about 0 Kelvin? If I start at 0 Kelvin, what can I say about this semiconductor? Let's say I have a kind of a dopant, an N-type dopant, or let's say a column 5 dopant, a donor. That would result in a piece of semiconductor that has more electrons than holes. And for that, because electrons are negatively charged, we call them an N-type semiconductor. Okay? And if you have more holes than electrons, we call it a P-type semiconductor. Now, N and P will lowercase n and lowercase p will be used to demonstrate the density of electrons and holes in a piece of semiconductor from now on. Okay. Now, one thing that's interesting though is that let's say we look at it versus temperature. So let's look at the number of electrons versus temperature in a piece of N-type dope. So basically we have some sort of column 5 donor introduced into the semiconductor with a density of Nd. So these are all per cubic. It should be really per cubic meter, but almost everyone in there, I really don't like this, but almost everything in semiconductor physics is done in cubic centimeters. Go figure. But we'll do it in per cubic centimeter, but I really don't like it that way. So now at 0 Kelvin, so let's say this is 0 Kelvin. By the way, there's no 0 degrees or 1 degree Kelvin. You never do it that way. Kelvin is the unit. So it's 0 Kelvin. At 0 Kelvin, what is N? 0, right? There's no free electron at this point. Now, as I raise temperature, what happens? Gradually, I'll have more and more electrons that have enough temperature, enough energy to form electron hole pairs. So I start going, this starts growing up, right? What happens when I get to Nd? So this is what happens. So initially, what happens is that nothing is ionized. Well, this is picture for the. So this is the donor case. Ed. So initially I have not enough energy to ionize anything. But as soon as I start raising the temperature, these guys can easily get ionized. So that's these guys starting to get ionized, right? Now, once I have enough energy, almost all of them will be ionized. Then I run out of these dopants, right? I mean, I don't run out, I mean, basically they're all ionized. So at that point, this becomes flat versus temperature. So there's a range of temperature where this is flat. And at some point, what do you expect? Do you expect this to be flat forever? You expect it to go back up at some point, right? Why?
Because it'll start breaching that lower.
The big gap, the
Right.
band gap, right? Exactly. So you will have enough to cross this barrier. And that's what would have happened if you didn't have the dopants. If you didn't have the dopants, if you had a pure piece of semiconductor, that would be the density of electrons versus temperature. But now, by introducing these dopants, you've created this region in which the number of electrons is controlled not by temperature, but by the number of dopants that I have introduced in my piece of semiconductor. And is that a good thing or a bad thing? It's a good thing. Of course, it depends on what you're trying to achieve. But then, yeah, for what you're trying to do is a good thing, because this is the region you want your device to operate in. Because then it's a well-controlled region of operation. Now, if I want to make a high-temperature semiconductor, if I want to make a semiconductor a transistor, let's say, that works at 200 degrees Celsius, right? What do I need to do? What do I need from my semiconductor? What kind of property should my semiconductor have? Exactly. Large band gap, right? Because the larger the band gap, the later this happens. Because it takes more energy. So the larger the band gap is, the more high temperature the semiconductor is. And that was one of the problems with germanium. You know, 40 years ago, 50 years ago, there were a lot of germanium transistors. Actually, when I was a kid, I used to make these kits with germanium transistors. And there was some silicon transistors, but there were a lot of germanium. But the problem with germanium transistors is that once they get over 60 or 70 degrees Celsius, they start dropping out. And it's simple because here, it's not a p-type, it's not an n-type piece of semiconductor. It behaves like a pure piece of semiconductor at higher temperature. Because you pretty much have the same number of holes and electrons because they're both generated thermally. They're not due to the dopants, right? And that's why you want to be operating in this region. And silicon has a higher band gap, and there are semiconductors with much higher band gap. There are compound semiconductors, and we didn't talk about those, but you can take elements from the third column, for instance, and elements from the fifth column, and make it compound semiconductor, a lattice. So every other atom is one of these. For instance, you can make a gallium arsenide combination. That would be another semiconductor. We can take indium phosphide. And there are other more. So those are called compound semiconductors. But again, even in those cases, you will have the same situation. Okay, any questions so far?
Oh, why use boron as an acceptor for silicon semiconductor? Oh, why not aluminum or why not?
Oh, okay, so that's purely material science. So the thing is that boron, you can make an alloy, a better alloy with boron than aluminum. If you introduce aluminum, you create a crystal defect in the semiconductor that creates this additional energy level, for instance, here in the middle. The trapped energy levels, which are really bad because they're very slow and create holes in electron recombination generation center. And we'll see why those are problems. So it's purely material science. Any other questions? We talked about this. Okay. So now we can talk about carrier distribution. So now, one of the important so far, what we've been talking about, we just refer to this thermal energy, right? We said, well, thermal movement, ionization, all that. But we didn't quite talk about it quantitatively. It was very qualitative. So let's do it a little more quantitatively. Now, electrons are fermions, right? So they follow Fermi-Dirac distribution. So this is if you look at the problem, you want to find the probability of finding an electron with energy E. That's given by Fermi-Dirac distribution, which is Fermi-Dirac. Okay. Now, if you look at it and at different temperature, so this is versus E, so this is F of E versus E, and look at it at 0 Kelvin, at T equals 0. How does this distribution function look? At temperature, at energies below EF, so this is EF. So let's say E is smaller than EF. What happens? This is smaller than that, so this is a negative quantity. T is 0. This is infinite, minus infinity. E to the minus infinity is what? 0. This is 1 divided by 1, so it's 1. 1 up to here. And then, if this is greater than, if E is greater than EF, what happens? This becomes positive, positive infinity, E to the positive infinity, infinity, 1 over infinity, 0. Of course, if there's a mathematician in the crowd who go crazy. 1 over infinity, 0 over infinity. You have to talk about limits and all those things to see the issue. You know what I'm talking about. So that's a T equal 0. Okay. Now, how about larger temperatures? Well, at larger temperatures, it's not as abrupt. So it starts from here, then you have a transition here. And EF is really the energy at which the probability of finding an electron is exactly 1/2. That's in a way the definition of the Fermi energy. EF is called the Fermi energy. So, what does that tell you? It tells you that there's a certain probability of finding electrons with certain energy at a given temperature. So it tells you that at 0 Kelvin, there's probability of 1 finding electrons below this, and there will be no electrons above that. Or no fermions in general, in this case electrons. But now, this is all good and fine, but there's an approximation that's quite useful, and for all practical purposes that we deal with, is very good. I mean, it's an excellent approximation. So let's look at one case, special case. So let's say E is greater than EF by at least 3 kT. So it's the difference is more than 3 kT. And think about it, 1 kT at room temperature is about 25 milli electron volts. So it's not a whole lot. It's 75 milli electron volts. So if that's the case, what can I say about this argument of the explanation? It's greater than 3, right? Because this is greater than 3 kT, this is kT, this is 3. So it's e to the 3, which is about greater than 10. So pretty much this becomes the dominant term, if that holds, right? So approximately, what it means is that Fe will be approximately E2 minus EF over KT to the minus sign. So this becomes a dominant term, and you have 1 over that, so I get the minus sign. Right? Which is proportional to, if I drop the second term, E2 minus E over KT. What kind of a distribution is that? The big guys. Really clever guys. Boltzmann. Boltzmann distribution. It's basically what it says is that above 3 kT here, I mean, if this distance is 3 kT, above here these are pretty much coincide, and below that it does something like this. Right? So, and you will see, in most of the situations we are dealing with, we are interested in this energy distribution way above 3 kT of the EF. And in those cases, you really can use the Boltzmann distribution. One of the interesting things about a lot of books and courses on device physics is that they go through everything with the Fermi-Dirac distribution. They make you suffer through all these kind of calculations through those. And then at the end, they make an approximation that's equivalent to saying that this is greater than that. So, and then they introduce this to what you would have gotten from the Boltzmann distribution. So we might as well make an approximation up front if we can. If we can, of course, we have to use this. We understand this is an approximation and this is accurate. So this is Boltzmann. You know what it says on his tombstone? It's the basic definition of entropy, right? That's the only thing that it says. Actually, you know, in his lifetime, nobody appreciated what he did. Nobody appreciated him. Everyone thought he was crazy. But just too bad. Now, there's something else that I'd like to talk about too. So now let's say EF minus E is greater than 3K. What happens in that case? Now, if EF is greater than E, so this means it's a negative quantity. So this becomes a very small quantity, right? So it's 1 over 1 plus a small quantity, which is approximately what? 1 minus that small quantity, right? Now, what is this? This is the probability, let's say, of not having an electron, this part of it. So this is the probability of having an electron. 1 minus that is the probability of not having an electron. What is the probability of not having an electron in the context of this semiconductor structure? Where do we care about not having an electron? When we deal with holes, right? So, in a way, you can think about this as a probability of finding a hole. And that's the approximation associated with the lower end of this thing. And we use this approximation. Now, there's one more thing. Now, so let's say something follows the Boltzmann distribution. I am interested in one quantity. Let's say I'm interested in finding what is the probability of finding, let's say, an electron with an energy higher than a given energy E1. What is the probability of finding an electron with an energy higher than E1? Basically, I want to find the area under this curve, right? What is the area under that curve? I know, so let's say f of E greater than E1 is, let's say, it's proportional to integral from E1 to plus infinity of that quantity, right? This quantity. So it's E to E minus df over kt with a minus sign. Well, there's a constant part to it, so I'll take that out. It's minus plus df over kt. And then I have to calculate this integral. E1 to plus infinity of e to minus d over kt. Oh, this is dE. Okay, and what's that integral? It's quite easy to calculate, right? I mean, so it's kt, minus kt comes out, and then you have the same thing, evaluate it from minus E1 to plus infinity. At plus infinity, it would be 0. So all you get is this to the minus E1 over kt with a minus sign, but you have another minus sign from the integration because of this thing coming out. So it essentially becomes, and I drop the kt that comes out of the integral. So this becomes proportional to e to ef minus e over kt. So what it tells, I'm sorry, E1. EF minus E1. So it says the probability of finding an electron, in this case, with an energy higher than E1 is proportional to that. Why do I care about something like that? An electron with an energy higher than a certain level. Where would that be useful, for instance? In this picture, for the sake of argument. Here.
Right in the lower edge of the conduction.
Right, exactly. So if E1 is here, then I can calculate the total number of electrons that end up here. Just because of the thermal energy. And that's very important when we see, actually, you can pretty much use just this, and some basic assumptions about the physics, to calculate the equate the behavior, and to come up, derive the general expression for the diode, the junction diode, the BJT, the current IV characteristic of the BJT on the diode. And you see, there's this, if you remember, it's the QVD over KT, right? That comes from this, and we'll see that, we'll do that later. But just keep this in mind. Okay, so there's one more thing, there are a couple of other things that you can actually derive from this using this expression. Now, one of the interesting things that it says, well, as we just said, is that, for instance, if you want to calculate the top, what is the total number of electrons? 3 electrons. How do I do that? Well, let's say n, the total number of electrons, is going to be what? Let's say it's proportional to what? Using this expression. As you pointed out, I need to just replace E1 with what? EC, the edge of the conduction band. So this becomes proportional to EF minus EC over KT. And I need a proportionality constant to get this right, and that's called NC. It's also called the density of state in the conduction band. You can actually derive that quantity, but we won't do that for our calculation. Now, you can do the same thing for the holes. For the holes, I need the probability of not having an electron below this energy. Right? And when I do that, again, it becomes proportional to, from the second part of that expression, it becomes proportional to what? EV minus EF, the valence band. And the proportionality for that is NV. Right? So these two should not be surprising. I just got it from the other ones. I just plugged in two proportionality constants. Right? It's clear where I got these two. Okay. Now, if I have a pure piece of semiconductor, a temperature 2, what can I say about the relationship between the N and P? N and P. The number of holes and the number of electrons. The pure piece of semiconductor, right? Intrinsic should be equal, right? They have to be equal, because they're generated in pairs. So now, this quantity we call also Ni, for intrinsic. Now, in that case, I know that Ni is what? Is Nc E2. Now, also we call the Fermi level for the intrinsic piece of semiconductor EI, where the Fermi level falls for an undoped piece of semiconductor, minus EC divided by KT, which is equal to NV E2 EV minus EI over KT. Okay? Now, well, let's say I have, and this is not necessarily undoped, so let's say I have a doped piece of semiconductor. What can I say about that? Well, let's see what I can say about N. Well, let's see if I can write N in terms of Ni. Okay? I know N in terms of Nc, but Ni is a better quantity because Ni is something that you can look up in the table, right? It's the intrinsic number of electrons at any given temperature versus for any piece of semiconductor. It's not going to change with the shape or the properties of semiconductor. This is not going to change with the shape either, but that's an easier quantity to measure, to look up, I guess. So I want to relate it to that. How can I do that? I want to rewrite this in terms of Ni. So what I notice that here I have what? I have two terms out of the three terms I need. I have the Nc and e to the k minus Ec over Kt. Right? So that part of this I can absorb, and all I need to do is just have minus that. So instead of this, I can write it as Ni e to Ef minus Ei over Kt. And similarly for the P, I can write it as Ni e to Ei minus Ef over Kt from that part. Okay? So what this tells you is that you can actually calculate the number of electrons or the holes if you know the relative location of the Ef and Ei, the Fermi level and the intrinsic Fermi level. Or conversely, if you know N and P, you can calculate where Ef and Ei are. Well, Ef is, Ei is at a fixed place. That's what the intrinsic level. It's not going to change with load. Now, these two also tell you something more interesting. Let's look at this one. The product of the two. What is the product of these two? Ni squared. These two cancel. So it tells you that for any piece of semiconductor in steady state, right, when you don't have a constant source of electrons or holes, or you don't generate them constantly, you don't recombine them constantly, the product of the N and P is constant, and in fact, it's Ni squared, which is the product of N and P in intrinsic undoped piece of semiconductor. And that's quite important. Okay? stop because the next topic is the motion of freight carriers. We'll talk about the drifting diffusion and all that kind of things, and then we'll go to the next time we'll start talking about it in But to summarize here quickly, is that what we did today, we looked at a very simple, yet sufficient for what we want to do, model for semiconductors. We saw that the energy levels are discrete, they're quantized energy levels. When you have multiple atoms brought together, what you get is energy bands, because you have so many energy levels, so close to each other, that they form an energy band. And then when you take this, and depending on the kind of material, you can have a situation where you have just enough band gap so you don't have a whole lot of electrons and holes, and you can control the number of electrons and holes in a piece of semiconductor by introducing these impurities, these dopants, into the material, and you identify two kinds. One is a p-type, the column 3s, which will generate more holes, and the column 5s will generate more electrons. So you had a way of engineering the material so that you could have regions with more electrons or more holes, at least in the intrinsic region. And then next time, one of the things we'll see is what you can do by placing these kinds of materials of different kinds next to each other, what kind of devices you can make, and we'll take it from there. Of course, the other thing we also saw is this distribution. One of the things to keep in mind, this is the distribution function. Of course, one of the things you have to always multiply this by the density of available states. So if you look at the Fermi energy level may be middle exactly here, yet you will have no electrons here because there are no available states. This is a band gap. So the total number of electrons is given by the product of the probability density and the density of states. We'll talk about that a little bit more next time. Any questions? No questions? So, yes.
Is there a lab part of this class?
No.
Okay.
There's no lab, but we'll do a lot of design work with, simulation work with these slides, but we don't do lab in this course. All right? One more time for those who came late. 304 is where you can pick up the handouts. I think are there any extra handouts? There's one there, so you can get one. And if you want a handout, you can pick them up from a drawer in room 304 upstairs. And that's it. I guess I'll see you on Friday.